This video will review the three common section properties used in stress calculations. You used these in ME 202 Strength of Materials, so this should just be a review for you. First, I will discuss the section properties used when calculating bending stress. Bending stress is calculated using the equation mc over I, or m over s. The letter I is used to refer to the area moment of inertia, and s refers to the section modulus. Second, I will explain the section property used when calculating transverse shear stress. Transverse shear stress is calculated by the equation VQ over IT. The letter Q is the first moment of area above or below the point of interest. Third, I will explain the section property used when calculating torsional shear stress. Torsional shear stress is calculated by TC over J. J is the polar moment of inertia. Let's begin with item number 1, area moment of inertia and section modulus. To help you understand the concept of moment of inertia, consider this question. Which beam would be stronger in bending? This beam is supported on each end with a load at the center of the span. The beam is 2 inches wide and 6 inches tall. This beam is the same size and has the same load at the center of the span. The only difference is that it is oriented horizontally instead of vertically. It is 6 inches wide and 2 inches tall. Your intuition should tell you that this beam would be much stronger. Beams loaded in the center will bend like this, causing a maximum tensile stress in the middle of the beam at the bottom in this direction. The tensile stress is calculated using mc over I. I is the area moment of inertia of the beam's cross-section. You will find that the beam oriented vertical is stronger because it has a larger moment of inertia. Let me explain why. This equation for bending stress has moment of inertia I in the denominator. Moment of inertia is a combined measurement of the amount of material and its distance from the neutral axis. As I increases, the bending stress will decrease. Let's compare the beam oriented like this with the beam oriented like this. Material that is furthest from the neutral axis adds the most strength to the beam. This material is closer to the neutral axis, which is why this beam is not as strong. Notice how we calculate I for a rectangle. BH cubed over 12. The height of the beam is cubed, showing that taller beams will have much higher moments of inertia. For instance, I for the tall beam would cube the 6-inch height, resulting in a moment of inertia of 36 inches to the fourth. I for the wide beam would cube the 2-inch height instead of the 6-inch dimension, resulting in a moment of inertia of 4 inches to the fourth. When you compare these moments of inertia, it's pretty clear that the tall beam is much stronger. Be careful though. We may be tempted to think that the tall beam is 9 times stronger, which is not true. Let me explain why. Even though this equation for bending stress includes I, it does not tell the whole story. It also includes C, which is also a contributor. C is the distance from the neutral axis to the outermost fiber of material. C is 3 inches in the tall beam and 1 inch in the short wide beam. Both C and I are contributors. Is there one single property that we could come up with that would tell the whole story and include the contribution of both C and I? A property that would be directly related to the strength of the beam, one that would allow us to compare one beam with another to see which is stronger. Let's take this equation for bending stress and rewrite it like this. If you think about it, you will see that these equations are mathematically the same. What if we were to define a new variable s, which was equal to the I over C ratio? Now we have one single property that is a direct measurement of the strength of the beam. We call this property section modulus. We could calculate s for the tall beam by taking the I over C ratio, which would be 36 inches to the fourth divided by 3 inches, resulting in a section modulus of 12 cubic inches. The section modulus of the short wide beam could be calculated the same way. 4 inches to the fourth divided by 1 inch, resulting in a section modulus of 4 cubic inches. If we compare the S for each beam, we will find that the narrow tall beam is 3 times stronger than the short wide beam, not 9 times stronger, which we were tempted to think when we compared the moments of inertia. Here is a page from the Machinery's Handbook showing a table of different size I-beams. Notice that it includes properties for bending about the x-axis, shown here, and properties for bending about the y-axis, shown here. The table includes moments of inertia as well as section moduli. Let's look at this 10 by 30 I-beam as an example. The section modulus for the beam when oriented upright is 32.4 cubic inches, and the section modulus for the beam when oriented on its side is 5.75 cubic inches. The upright orientation of this I-beam is 5.6 times stronger than if it was oriented on its side. This page on the right shows section properties for C-channel. Let's compare the section modulus of the 10 by 30 I-beam with that of the 10 by 30 C-channel. We can see that the I-beam is 1.6 times stronger than the C-channel, even though they are both the same nominal height and weight. Understanding section modulus allows us to make such comparisons quickly, which is useful in making design decisions. Now let's review how to calculate both I and S of a hollow rectangular tube. We can find the overall moment of inertia by taking the moment of inertia of the outside rectangle as if it were solid and subtracting out the moment of inertia of the inside rectangle. I of the outside rectangle is 4 times 6 cubed over 12. Calculating I for the inside rectangle will require us to find the inside dimensions of the tube. If we subtract two wall thicknesses from the 4-inch width of the tube, we will find that the inside width is 3 inches. Similarly, we would subtract two wall thicknesses from the height to find that the inside height of the tube is 5 inches. We can use these dimensions to calculate I inner, 3 times 5 cubed over 12. The overall moment of inertia of the hollow tube is 40.8 inches to the fourth. The section modulus S is simply the I over C ratio. Remember, C is the distance from the neutral axis to the outermost fiber of material. An I of 40.8 inches to the fourth divided by a C of 3 inches equals 13.6 inches cubed for the section modulus. Now let's review how to calculate I and S of a round shape. If you did the calculus, you would find that I for round shapes is 1/4 pi r to the fourth. S for round shapes is simply the I over C ratio. I is 1/4 pi r to the fourth, and C, the distance from the neutral axis to the outermost fiber of material, is simply the radius. After a little algebra, we see that the section modulus for round shapes is simply 1/4 pi r to the third. Calculating I and S of hollow round tubes is simple. We just take the I of the outer circle as if it were solid and subtract out I of the inner circle. Since the outside radius of this tube is 4 inches, I of the outer circle is 1/4 pi times 4 to the fourth. I of the inner circle requires us to determine the inside radius of the tube. We can simply subtract the 1-inch wall thickness from the outside radius to find the inside radius of 3 inches. The I of the inner circle is simply 1/4 pi times 3 inches to the fourth. The overall moment of inertia for this round tube is 137.4 inches to the fourth. The section modulus is just the I over C ratio, 137.4 inches to the fourth divided by 4 inches, resulting in a section modulus of 34.4 inches cubed. Now let's review item number 2 in our agenda, the section property used in calculating transverse shear stress, Q, which is the moment of area above or below the point of interest. Remember our discussion for the rectangular beam loaded at the center of the span? It bends like this, and we determined that the maximum tensile stress occurred here at the middle of the beam along the bottom. We calculated that tensile stress using MC over I. Understanding transverse shear stress requires us to think about the reaction forces. The reaction at the left end would be P over 2. The reaction at the right end would also be P over 2. Not only would the beam bend, but the reaction on the left side will try to shear the beam like this. We find that the resulting shear stress is 0 on the outer fibers of material, and maximum here in the center of the beam. The shear stress on this face is in this direction, which means the shear stress on this face is in the opposite direction, and shear stress is automatically developed along the top and bottom faces of this element in these directions to keep the element balanced. These shear stresses are called transverse shear stresses, and are calculated with the equation VQ over IT. Q is the section property we are reviewing in this portion of the video. You have noticed that I described Q as the moment of area above or below the point of interest. The point of interest is usually the location where Q is the highest, and would result in the maximum transverse shear stress. Here is the cross-section of the beam. The point of interest is usually here at the neutral axis, where transverse shear stress will be the highest. Now let me explain what is meant by moment of area. Taking the moment of something means determining the leverage of that thing. For instance, taking the moment of force is the leverage of force, or force times the leverage distance. Therefore, the moment of area is the leverage of the area, or the area times the leverage distance. So now let's review how to calculate Q of a rectangular shape. The point we are usually most interested in is here at the neutral axis, since that's where the transverse shear stress is highest. And Q is the moment of area above or below this point of interest. Let's take the moment of area above. If we did below, we'd find it's the same number. So we just take whichever is easiest. Moment of area is simply the leverage of the area, or area times the leverage distance. The area is this that I am showing in blue, which is 2 inches wide and 3 inches tall. 2 times 3. The leverage distance of this area is the distance to the center of area as if the neutral axis was the fulcrum. In this case, that distance is shown here and is 1.5 inches. Multiplying by this distance results in a Q of 9 cubic inches for this rectangular shape at its center. Now let's review how to determine Q for round shapes. Again, Q is simply the moment of area above the point of interest. Moment of area is the leverage of the area, or area times leverage distance. The area is shown here in blue, which is half of the circle. Pi r squared over 2, since it's only half the circle. The leverage distance of this area is the distance to the center of area as if the neutral axis was the fulcrum. You can look up in your ME 202 textbook that the distance to the centroid of a half circle is 4r over 3 pi, which is our leverage distance. If we do a little algebra to simplify, we can find that Q for a round shape at its worst case location is 2 times r cubed over 3. Now let's review how to find Q of hollow shapes. The overall Q can be found by taking the Q of the outer rectangle and subtracting the Q of the inner rectangle. Q outer is the moment of area, or outer area times leverage distance. Q inner is the moment of area, or inner area times leverage distance. The outer area is this that I have highlighted in blue. It is 4 inches wide and 3 inches tall, 4 by 3. The leverage distance to this area is this distance here, 1.5 inches. The inner area is this that I have highlighted in red. If we subtract 2 wall thicknesses from the width, we find the inner width is 3 inches. If we subtract 2 wall thicknesses from the height, we find that the inner height is 5 inches. And the height of this red area is therefore 2.5 inches. The inner area is 3 by 2.5. The leverage distance is this distance to the center of the red area, 1.25 inches in this case. So that the overall Q for this hollow rectangular tube is 8.63 cubic inches. So we have reviewed how to calculate Q in this equation for transverse shear stress. Earlier in the video we reviewed how to calculate I. But you may be wondering what T means. T is the total material thickness at the point of interest. Since the point of interest is usually at the neutral axis, since that is the location of highest transverse shear stress, the total material thickness at this point is 2 wall thicknesses. So T in this case would be 1 inch, not just a half inch. Now let's review item number 3 in our agenda, the section property used in calculating torsional shear stress. J is the polar moment of inertia. Torsional shear stress is caused when loads are placed like this on a beam and causes it to twist. The elements all around the outside perimeter experience maximum shear stress due to torsion. This element, for instance, if we looked at it closely, would have shear stress downward on this face, which of course would require an upward shear stress on this face, and shear stresses in these directions as well to keep the element balanced. We calculate this shear stress using Tc over J. This element is also on the outside perimeter and would have the same amount of torsional shear stress calculated by Tc over J. J is the section property that we are reviewing in this part of the video. It is the polar moment of inertia, which is a property of the cross-section which indicates the ability of the beam to resist twisting. Let's review how to calculate J for round shapes. You will recall that J is simply the sum total of the moment of inertia about the x-axis and the y-axis. This makes logical sense because Ix tells us how the material on the top and bottom contribute to strength, and Iy tells us how the material on the left and right contribute to strength. J is a measure of how the material all around contributes to strength, and so it makes sense that J is the sum total of Ix and Iy. Ix is the moment of inertia for bending about this axis, and for round shapes is 1/4 pi r to the 4th. Iy is the moment of inertia for bending about this axis, and for round shapes is the same as Ix, 1/4 pi r to the 4th. 1/4 plus 1/4 is equal to 1/2. So j for a round shape is 1/2 pi r to the 4th. J of rectangular shapes can be found in the same way, the sum total of Ix and Iy. Ix is the moment of inertia for bending about this axis, b times h cubed over 12. Iy is the moment of inertia for bending about this axis, h times b cubed over 12. If we do a little algebra, we can simplify this equation a little bit if we want. Finding j of hollow tube shapes follows the same pattern we have already reviewed. We can simply take the j of the outer shape and subtract j of the inner shape. J of the outer shape depends, of course, on the outer radius, and j of the inner shape depends on the inner radius. So we could do a little algebra to simplify this if we wanted. To conclude this video, I want to show you how CAD can be helpful in determining section properties. As a matter of fact, I have found that when I have challenging geometry, trigonometry, or section property problems to calculate, it is often a lot easier to just draw the shape in CAD and measure it rather than calculate it by hand. Here are 3 beams that I've modeled in SolidWorks. The first one here on the left is a 3-inch round tube with a 1/2-inch wall. The one in the center is a 3-inch square tube with a 1/2-inch wall. And the one here on the right is also a 3-inch square tube with a 1/2-inch wall, only it's been rotated up by 45 degrees, and we'd call this a diamond. To determine the section properties, we would come here to the Evaluate tab, and we would choose this Section Properties tool. You're probably used to choosing the Mass Properties tool. If I go here, let's clear those selections and choose just this round tube and recalculate. Notice that that is giving me the moments of inertia, but it's not the area moment of inertia. It's giving me the mass moment of inertia. Notice the units, pounds times square inches. So this is certainly not the moment of inertia we're interested in our stress calculation. We need to come here to the section properties. And the section properties are based on a cross-section. So in this blue area here, I can choose a cross-section by selecting either a sketch or a face. Let's select this face, which is the cross-sectional area of that beam. If I select Calculate, you'll notice that it's telling me that the cross-sectional area is 3.927 inches squared. It also tells me the moments of inertia of the area. The moment of inertia about the x-axis, 3.191. Moment of inertia about the y-axis, also 3.191. And we'd expect it to be the same since it's a round tube. It tells me the polar moment of inertia of the area, which is 6.381 inches to the 4th, which is the sum total of the Ix and the Iy. If I clear this selection, I can choose the square cross-section and recalculate. And notice that has a little bit higher moment of inertia, 5.417. If I clear this selection, I can choose the cross-section of our diamond and recalculate it. Notice it has the same moments of inertia about the x-axis and y-axis, 5.417. So we may be tempted to think that a square tube is just as strong no matter what orientation it's at. However, be careful. Remember, we don't compare just the moment of inertia to determine the strength of a beam. We compare the section modulus, which has to do with the I and the C. So if you wanted to compare these two, you'd have to compare the section modulus